we are interested in some notable solutions in congestion games. The first solution we are interested in is the solution minimizing the social cost, that we call the socially best solution. Notice that, in principle, the reasoning we propose in the following can be applied to any objective function, also different from the minimization of the social cost. The solution minimizing the social cost may be not a Nash equilibrium. Later we will see some examples. The second solution we are interested in is the Nash equilibrium minimizing the social cost. Basically, this solution is obtained from over-constraining the previous problem. That is, we are looking for the solution minimizing the social cost subject to the constraint that is a Nash equilibrium. Finally, we are also interested in the Nash equilibrium that maximizes the social cost. Obviously, the relationship holds in this way. The socially best solution is the solution with the minimum cost. Then we have the Nash equilibrium with the minimum cost. In principle, the inequality may be strict. Finally, we have the Nash equilibrium maximizing the social cost. Also here, the inequality may be strict. On the basis of these solutions, we can define some indices. The first index is called price of stability, and it is defined as the ratio between the socially best Nash equilibrium and the socially best solution. Obviously, this ratio is always larger than or equal to 0. That is, this index provides a measure of the inefficiency of a Nash equilibrium. In other words, in practice, we could like to minimize the social cost, but since the players are rational, we cannot reach the minimum social cost. We will reach a cost a bit higher than the minimum, and this is because the players are selfish. That is, we need to pay something to have the stability of the strategy of the player. Similarly, we can define the price of anarchy. This index is defined as before, except that in place of the best Nash equilibrium, we have the worst Nash equilibrium. The meaning of this inefficiency index is rather intuitive. Suppose that we cannot control the best response dynamics of the players. This index returns the maximum inefficiency the players can achieve. Obviously, we have that 1 is smaller than or equal to the price of stability, that in its turn is smaller than or equal to the price of anarchy. Here you have the complete framework. The power of the model based on congestion games is that the players can reach easily and autonomously Nash equilibrium, and they can do that very quickly. However, we cannot know, before the conclusion of the best response dynamics, the Nash equilibrium they will reach. So our interest is in characterizing the spectrum of Nash equilibria they can reach, identifying the socially best and the socially worst. Such a characterization is especially important when we can design the problem. For instance, when we can design the routing network or we have a budget to reduce the cost of the resources or to add new resources to the problem. Consider this simple example. We have 3 access points, denoted with antennas. Each antenna covers a limited area. We have 3 players, denoted with the orange circles. Assume for simplicity that the cost of each player in connecting an access point is equal to the congestion. Here we have the socially best solution, where each user has a cost of 1 since each user uses a different resource. So the social cost is 3. Interestingly, this is also a Nash equilibrium. Indeed, if every player switches, the cost strictly increases by 1. So the social cost in the best Nash equilibrium is 3. However, there is a Nash equilibrium where the social cost is 5. That is, we have 2 players with a cost of 2, while a player with a cost of 1. So we have that the price of stability is 1 in this case, while the price of anarchy is 5/3. That is strictly larger than 1. Now, consider the example. We can show that the price of stability is unbounded in the number of resources, and therefore also the price of anarchy is unbounded. In this example, we have n players. Each starts from a different node. Specifically, the node has I denotes the starting point of player I. All the players must reach the same sink, that is the node B. Notice that each player can decide to reach the sink directly or not. In the direct case, the cost of player I is equal to 1 divided by I. So player 1 has a cost of 1, while player n has a cost of 1 divided by n. Or the players can decide to go to node A and subsequently to the sink B. In this case, the cost to reach A is 0 for all the players, while the cost to reach B from A is equal to 1 plus epsilon divided by the congestion. So the larger the congestion, the smaller the cost of each player. But the social cost is the same independently of the congestion. Here the socially best solution. All the players go to A and subsequently to B. The social cost is 1 plus epsilon. However, we can see that the solution is not a Nash equilibrium. Indeed, focus on player n. Her cost in the socially best solution is 1 plus epsilon divided by n. However, if she switches, her cost is 1 divided by n, so the player switches. Now focus on player n minus 1. Here the reasoning is the same as before. The cost she will get in this case is 1 plus epsilon divided by n minus 1. But if she switches, her cost is 1 divided by n minus 1. So the player switches. And so on. Until every player has switched. This leads to social cost that is given by the sum of the cost of all the players. That is 1 plus 1 half plus 1/3 and so on. The sum is asymptotic to the logarithmic of n. Thus, the cost of this equilibrium is unbounded, being asymptotic to the logarithm of n. And therefore, the price of stability is asymptotically unbounded in n. Many nice properties of the congestion games are due to the existence of the potential function. A natural question is whether we can define game classes admitting potential functions that are not congestion games. We introduce some classes of potential functions. The first class contains the exact potential function. They are those such that for every switch of player I, the difference of the potential function is equal to the difference of the cost of player I. The congestion games are game admitting an exact potential function. Then we have the weighted potential function. They are such that for every switch of player I, the difference of the potential function is equal to the difference of the cost of player I multiplied by a weight wi. Finally, we have the ordinal potential functions. Here we have that for every switch of player high, such that the cost of player high reduces, also the potential function reduces. Notice that every exact potential function is also a weighted potential function. Indeed, it is sufficient to set all the weights equal to 1. The vice versa instead does not hold. Furthermore, every weighted potential function is also an ordinal potential function. Also here, the vice versa does not hold. In order to assure that a game admits a pure strategy Nash equilibrium, it is sufficient that such a game admits an ordinal potential function. Furthermore, if all the best response paths of a given game are finite, then it admits an ordinal potential function. To conclude, we provide a characterization of all the games admitting an exact potential function. Initially, we introduce a class of games called coordination games. In a coordination game, all the players have the same utility function. In the slide, it can be observed that in every cell of the biometrics, the utility of both players is the same. A dummy game is a game in which the utility of a player does not depend on her actions, but only on the actions of the opponent. Consider the biometrics in the slide. Focus on player 1. In every column, the utility of the player is constant. Similarly, in every row, the utility of player 2 is constant. A normal form game admits an exact potential function if and only if the utility of every player is given by the sum of two utility functions, such that the game with the first utility function is a coordination game, while the game with the second utility function is a dummy game. We prove the result. If UIA is equal to UICA plus UIDA, then the potential function is equal to UICA. Indeed, if player high switches, UIDA does not change, and therefore the difference of the potential function is equal to the difference in UICA. Assume instead that the game admits an exact potential function. Set UICA equal to the potential function. Set UIDA equal to the difference between UIA and the potential function. The game with UICA is a coordination game, since all the players have the same utility. The game with UIDA is a dummy game, since the difference of the utility of a player when she switches is equal to the difference of the potential function, if and only if UID does not change, and therefore UID is a dummy game.